Now, there's some more PFC balls. I went to Finland some years back. I get there, the guy picks me up at the airport and he drives me to the train station and he says, "Look, we're greeting you because we got the PFC balls. We just finished constructing that thing and put those PFC balls in there." So there we go. Um, oh yeah, here's some more. This is from at the University of Vienna, right? See, that's what it feels like sometimes. It's like the weight of the world on your shoulder when you're trying to run PFC. Um, all right. Now, before we do this, we have to do a little bit. I'm going to give a little bit of thinking about modeling, okay, and microstructural modeling, okay. Um, so I like this one. In order to comprehend that which is incomprehensible because it is too huge or too complex, one needs simpler models. Often mathematics can provide the right starting point, which is why beautiful mathematical concepts are so pervasive in explanations of the phenomena of nature on the micro level, right? You could all basically say we're understanding the micro level of behavior because Newton gave us F equals ma. Everything, everything about these systems is following because of that, actually. Um, okay, why are we modeling? This is the question you always have to ask yourself. What is the objective of the model? And so I'm going to say there's three things we're doing. We're basically creating a synthetic material and maybe even a system. So the synthetic material might be the sandstone, the system might be the rock cutter. So we're creating a synthetic material, we're subjecting it to some kind of loading, and we're monitoring the response. That's predicting the behavior, right? But that's what we do with the model. And the question is, we want to use it then to do these different types of things, right? Do parametric studies, investigate what if scenarios. What if the amount of cement was only 1/2? What would that do, right? And test different mechanistic hypotheses, right? What's really the effect of fluid pressure? What if the pressure was distributed differently? Um, in order to really have any faith that your model makes sense, you have to have some concept of validation, right? The model is going to run and give you predicted behavior, but the real question is that behavior the real behavior of the physical system, right? In this material modeling support memo, which you will become familiar with if you actually start using this package, um, there are 5 papers that we refer to at the end of this section 1. And these papers talk about this whole concept of verification and validation. And it would be useful. You may find them to be of interest, and you may want to look them up. And those papers should be in all those sets of papers that I provide you with. Okay. Um, verification. There's 2 aspects of this. Verification means that you have a model. We have a model. Our model is rigid bodies that are interacting with each other, and they're following the mathematics of F equals ma. And so our model is actually this. That's really what the model is. It's not rock, it's this. Um, and so the first question is we need to verify that our model is really behaving like this. And that's essentially what gets done by us. And we have verification problems, for example. So we confirm that, yes, you construct a system of tennis balls that are masses connected with springs, and our model's going to do the same thing. Okay, that's verification. But what we really want to know is validation, right? Is this actually a useful representation of the real world, right? So the first thing is just mathematics. The next thing is physics, right? So the question is this useful for you to understand the response of rock, right? That's the validation part, okay? Um, this is a book that is the best book I have ever read about the philosophy of modeling, okay? And this guy is super interesting because this guy was originally a computational physics professor, and then he became a professional philosopher. And so he's addressing from a fundamental point of view, what is it that we get from computer simulations and how do we gain confidence that they make sense? And he uses weather prediction and fluid mechanics stuff as a description of this. And he talks about like these weather prediction models, right? Like, how do we know that they're right? And he develops this concept, he calls it sanctioning, which really means how do we gain confidence, right, in the results? And this is tricky. And let me just read you the quote that I pull out of this thing here. The sanctioning of simulations does not cleanly divide into verification and validation. That's too simple. In fact, simulation results are sanctioned all at once. Now think of this in terms of simulation results of giant weather forecast models. In fact, simulation results are sanctioned all at once. Simulationists try to maximize fidelity to theory, to mathematical rigor, to physical intuition, and to known empirical results. But it is the simultaneous confluence of these efforts rather than the establishment of each one separately that ultimately gives us confidence in the results. Okay. Here is another, before we get to this, let's go up. Yeah, let's talk about this one. This is another interesting book. I'm quite interested in baseball. And there's a book called The Physics of Baseball. And this was written by a physicist who actually was personal friends back in 2000 with the commissioner of Major League Baseball. They were personal friends. And the commissioner said, "You are so good at explaining basic things of mechanical behavior, and you're a baseball fan, you should write a short little book that anyone can understand that addresses things like the physics of baseball," right? You know, if it's a humid day, does the baseball really not fly as far? Things like that. And so at the beginning of this book, he's writing this to people that don't know anything about physics or baseball, right? And so he needs to basically say, what are the constraints? What is he doing? How is he using these models? What do these models mean? And let me read this one because this is such of a good description of modeling. In his analysis of a real system, a physicist constructs a well-defined model of the system and then addresses the model. So he says, okay, the system we address here is baseball. Now, it's complicated. We cannot calculate from first principles the character of the collision of an ash bat with a sphere made up of layers of tightly wound yarns, nor do we have any precise understanding of the effect of the airstream on the flight of that sphere with its curious yin-yang pattern of stitches. This is what the baseball looks like. It's stitched together. It's leather stitched together with a whole bunch of wound together string on the inside. But what we can do is construct plausible models of those interactions that play a part in baseball that do not violate basic principles of mechanics. Though these basic principles severely constrain such models, they do not completely define them. It is necessary that the models touch the results of observations, or the results of the controlled observations called experiments, at some points, so that the model can be more precisely defined and used to interpolate between known results or to extrapolate from them. If the model is well chosen so as to represent the salient points of the real system adequately, conclusions derived from an analysis of the model can apply to the system to a useful degree, right? He talks about all the different aspects we've been talking about models, right? If the model is well chosen, if it represents the salient points of the real system, that's where I keep saying, does it have the basic micromechanisms that we think are the important things that are controlling the behavior? If it does all of that, you can actually get some useful information from it, right? He also talks about we have to have a physicist constructs a well-defined model. So what we have in this material modeling support package, there are these well-defined models of 5 different microstructures. Okay, contact bonded, parallel bonded, soft bonded, flat jointed, subspring networked. Going back to the sanctioning, how do we gain confidence in the results? Well, these PFC models for rock have been sanctioned, and really they've been sanctioned because we demonstrate that we can match the response during tension tests and during compression tests of typical rocks. And that's what I went through just 30 minutes ago when I talked about showed some of the behavior of the flat joint. Axial splitting in a UCS test, distributed tensile cracking aligned with compression during a UCS test, tension test, eventual fracture that's perpendicular to the thing, right? Matching the values of tensile strength, matching the values of compression, all that kind of stuff. That's how we sanction these things. Here's the simple idea again. If you have a contact bonded versus a parallel bond has this finite width of cement. You can think of, if you in the parallel bond, you control this radius. If you made parallel bonds with smaller and smaller radiuses, they would become like that's what a contact bond would be in the limit. In the limit, as that radius goes to 0 of a parallel bond, you get a contact bond. Okay. Again, the flat jointed microstructure is allowing you to have boundaries on that sphere that are angular, and those boundaries remain in effect even after it starts to break, and it can break partially. Here's this idea, right, where I rotate the top. These guys, these elements have broken. Those are in compression. They have not broken. This is that rotation. These are the contact forces that are building up. These are the contact forces acting in the system. Even though there's no bonding, there's still restraint because of that. Okay. We've shown this before. This was that very first computer, right? And this talks about the well-designed objects. There's a poorly designed object for you, right? We have visual clues. Okay, material modeling support. Let's begin. So, okay, what you have to work with is an assembly of rigid grains that are interacting at contacts, okay? The support for material modeling, it consists of this consistent set of functions, fish functions, and we call this the fish tank or the FIST package. Okay. What can you do with this system? What is the things you can create with this system? It's providing you with a model. So therefore, it's a well-defined model. It's providing you with a set of parameters that are going to give you in particular instantiation of that model, right? So what are the sorts of things, those parameters? Well, the grains can be either balls or clumps, and they're going to be drawn from a size distribution. You can specify that, okay? And then I'm going to call different sorts of materials based on the type of contact model at the grain contacts. Depending on the type, it's going to be, you know, parallel bonded, for example, right? We also have this linear material. It's just a granular material. It uses the linear contact model. There's no bonding in that, right? And so if my simple example, right, if these guys are not bonded using a linear model and I hit them, they break apart. They cannot sustain tension. They don't hold together. If they're bonded, you get these, they start moving and shaking, and now they're moving like a deformable body, and the compression and tension is going back and forth in there, right? This is just the same thing, showing it in 3D. Okay. So overview. The first thing that we have is we have a set of material vessels. That in 3D, that could be a cylindrical shaped vessel. There might be there's a parallel pipe edge shaped vessel, okay? And then there's this well-defined procedure that we go through to get the initial assembly that we're then gonna create bonding for. So that procedure is going to involve a packing phase, do something to get it connected nicely in a controlled way, and then finalization, which is now add all the cement, basically. There's these different materials, right? Parallel bonded material, flat jointed material. There's going to be some common material properties for everybody, like for example, the density of each grain. That's common to all the materials. But then there's of course going to be specific material properties for each one. The parallel bonded material properties have different parameters than the flat jointed ones, okay? There's built-in support for doing what I call microstructural monitoring. looking at damage, for example, looking at those cracks that form, visualizing that, drawing those fancy plots that I showed of the flat jointed materials, those things I called faced grains. And then there's these standard rock mechanics laboratory tests that we can perform. And so we're going to first talk about there's different ways that we can measure stress and strain and porosity, and then we can use those in the process of doing these tests. Basically, triaxial tests, Brazilian tests, which I'm calling diametral compression, and direct tension tests. And then what we provide to actually work with this, there's an example of each material. There's an example directory that has a material, like there's a parallel bonded material example. And in that directory, there's going to be a project that's going to let you create the material. And then there's going to be a subdirectory called tension test. And then there's going to be another subdirectory called compression test. And so in the compression test directory, there's a project that's going to restore the bonded system, and then it's going to go and do its test. And it's going to make save files along the way. It's going to have all the plots that you want to look at, like stress versus strain, radial stress versus radial strain versus stress, volumetric strain, all those things. Okay. So basically, we need to understand the basic stuff in here, and then to work with it, we take an example and then we modify it. Okay. This is just a high-level picture. This is all on the ITASCA website. You can download this material modeling support package. This is just giving you sort of a highlight of the kind of things that you do with it, right? So here's a parallel bonded cement system. Here's a bonded Voronoi grain system. Here's what you might measure triaxial tests on that material. Here is showing material that's been constructed inside of a parallel pipette material vessel. Those walls were moved outward after construction, and then the top and bottom walls were pushed, simulating a UCS test. And this is the broken bonds inside that system somewhere during that test. This is a Brazilian test being squeezed from above and below, and those are the cracks inside. This is a direct tension test. What we're going to do is define particles on top and control their velocities. The same thing on the bottom. We're going to slowly pull them apart, measure force and displacement, turn that into stress and strain, look at broken bonds again. Okay, that's essentially what you're doing with this. What we want to do is we want to be able to create a well-connected assembly at the beginning that is homogeneous and isotropic, right? So for example, if we want to build a specimen of rock, what we could do is take particles, turn on gravity, and let them settle and form a pile, and then we could bond them. If we did that, we would have a transversely anisotropic material, because the force chains are going to be aligned vertically, and that's going to be packed in such a way that's a function of how it got packed when the sand got put in there. What we have instead is a material creation procedure such that we're going to get isotropic system. We want it to be the same in all directions. Okay, and I'll tell you how we do that. And the way we're going to have to do that is we're going to have to basically press it in there at some pressure. Okay, and we want to try to, typically we want to make that pressure really low for that initial packing. What about the vessel walls? What about the vessel walls? What we're going to do in this package is we're always just going to use a linear contact model there. And those walls are going to be frictionless. And so if they're going to be frictionless, then the friction coefficient doesn't matter. And the shear stiffness doesn't matter. They're not relevant if they're frictionless. So the only parameter we need at that interface, so that's the ball facet type of contact, is the Kn, the normal stiffness. But instead of giving a normal stiffness, we're going to give a effective modulus, that E star thing. And so we're going to specify E star for that interface, the effective modulus. Okay. And the value we use for that should be essentially approximately equal to the final modulus of the material. Because what we want when what those walls are really doing is they're just applying forces to the system. And we want those overlaps between the walls and the balls to be relatively small. So we would get that if we basically set the wall modulus about equal to the material modulus. Okay. If the wall modulus is really low compared to the material modulus, then you're going to get these big giant overlaps between the walls and the balls, and we don't want that. Conversely, if the wall modulus is extremely high, you will not have overlaps. That's great. But you're going to have a very small time step, because remember, the time step is related to the stiffness in the system. And so if we have really high stiffness at that wall particle interface, those springs are going to be vibrating really fast. So there has to be a really small time step. So we don't want that. So what we want to do basically is tune down the modulus, the effective modulus of the wall, to be about equal to the modulus of the system. And whenever you're doing this, you know you have a target modulus for your material, so you know what this is. Okay. These are the provided material vessels in 2D. You can make this shape in 3D. You can basically make these shapes, a cylinder, or I call this a polyaxial cell. Okay. There's also a periodic cell where you can build material in periodic space. The cylinder, notice these compression platens are going to be made a little bit bigger than the size of the top of the cylinder, because remember, the walls do not interact with other walls. They only interact with the material. And this way we don't have to worry about these guys uh, pushing out at the corners here or something. Okay. And so then these are parameters, right? Alpha, the default alpha is 1.4 times W, right? The default height is this. Okay. Um, okay. Just one slide talking about this periodic business. If we make this system here, HW in 2D, periodic, what we will get is a packed assembly where this guy comes out, he sticks his nose in on this side. The result is that everybody on this side is fits perfectly with everybody on that side. And the same thing above and below, which means I can take this piece and I call that a periodic brick, and I can take it and I can assemble it together into a larger structure. So I can take this and stick one here, stick one next to it, stick one next to it, stick one next to it. This is the system. The result of replicating it 4 times is this. This system, if I get this packed at a small pressure, I can use that to build up a bigger material. Okay. You can do this kind of stuff in PFC. So sometimes if you want to build a big, huge assembly, you just work with a small periodic assembly and then you construct it boom, boom, boom to get your bigger assembly. If this is in equilibrium, when you can put it all together, it'll still be in equilibrium. Everything will be in balance. Okay. So we have, as I mentioned, we have a well-defined model here. So there are going to be parameters that are going to determine all the characteristics of the material vessel. And so here they are. So in that memo, there's a whole description of this, and here's the table for the material vessel parameters. So one of them, for example, is the effective modulus. Effective modulus of physical vessel. This is a symbol that I use for whatever that parameter is. And then this is the name of the fish variable. So these all start with MV underscore, which is for my shorthand for material vessel. So effective modulus, MVE mod. This is then the type. It's a floating point number. It's supposed to be in the range from 0 to infinity. Notice it's not supposed to be 0. This is not that means it includes this. This means it doesn't include 0. So it has to be a positive number, right? And then this is the, the description of what all these things are, right? So this is is it a rectangular? Is it a cylinder? Is it a sphere, right? Of the shape. It didn't show that before. You can also make a spherical vessel, okay? So here's then what that looks like. So here's the description in words of the parameters. Where do they live? Well, when you run the project, there's going to be a data file, and it's going to be mv_params.p3dat, material vessel parameters. In that data file, which you'll see on the next screen, you're going to basically give values to each of these parameters, or you're going to use the default values. There are default values for many of these things, not all of them. So for example, the height, width, and depth of your specimen, that's not applicable. I don't have a default. It's not available because I don't know. There is no default size. You have to choose the size, right? Right? The default is the expansion factor. This is this alpha that talks about this business. How far is this expanded relative to that size, right? By default, that's 1.2. Okay. All right. What did this look like? Here's what it looks like. There's the data file in the PFC editor. So also one of the things you're going to see in this package, in every file that's in there, it's going to have the first thing is going to be a comment. This is file name. That's a file name. The last line, EOF, end of file of the file name. So then here's our fish. Here's our fish define. This is called MV set parameters. Here we go. You're setting values for these guys. The ones you want to set, other ones are default. So what do I do? It define the fish function, and then this thing calls the fish function. This is older notation. This ampersand basically means treat this as a fish function. The more modern thing to do now is to use the square brackets around this thing. Okay. So this is going to call the function, and since you put the values, it's going to set those variables to be what you want them to be. Then this is an internal function somewhere. It's called check the parameters. And so this is going to do some checking for this stuff. If you give a modulus that's -6, it's going to say, sorry, the modulus needs to be between 0, needs to be a positive number. So that's doing the checking. And then this, listing the properties. So when this gets called, list properties, here it goes, material vessel properties. MV type, MV shape. These are all the different properties of the material vessel. And it's saying, oh, the MV type is 0. There, the MV effective modulus, 5E8, right? So this, first of all, because the plots, there's going to be a plot of axial stress versus axial strain. Well, what's the units of axial stress? As you know, PFC doesn't care about units. You can do any units that are consistent. However, with this material modeling package, I'm assuming you're using SI units because there's a plot that's already created that's going to say axial stress and it's going to say pascals. So I'm assuming that you're using SI units. Okay. There's also this thing I call a microstructural box. What this is going to do, and so this is defining the box. That's the center of it. This is the size in the X, Y, and Z direction of this box. This is going to be used, for example, to draw those fancy plots of the shape of the grains and stuff like that, and showing parallel bonds as cylinders and things like that. Okay. Because you typically just want to zoom in to the center and just look at, 5 or 6 little spheres. You don't want to see that weird fancy plot for every single guy of the 50,000 guys in your system. Okay. So the packing phase, what do we do? Here's what we do. You give a size distribution. And what you're going to do is give a size distribution, and you're going to give what we call a grain cloud porosity. This is what we were giving in when we did that distribute command. When we said ball distribute, and then we gave those bins, and we said, what's the volume fraction and the size of bin number 1? And what's the volume fraction and size range of bin number 2? So you're going to give that same information, and then it's going to say, okay, decide how many to do such that you get some porosity. And this is the porosity. It doesn't account for the overlaps. So when we were doing the 2D things, we were often using like 0.12. If we choose that porosity too high, then we just get a cloud of balls that are not packed. If we choose it super low, we get like incredibly high packed systems. Okay. So that's what you're going to specify. And then what they're going to do, the first thing is they're going to rearrange into a packed state with zero friction. Okay. So given them, you want to pack, they're going to get packed. They're going to get all packed tightly under zero friction. So they're going to be isotropically arranged because of that. Then there's a control here. You're saying, but what's the final pressure you want for this to be? So there's two ways to do it. You can basically contract the boundary, okay? And what you're going to then do if you're doing boundary contraction, that's where you're going to squeeze the walls in or out, okay? Is you're going to set the friction coefficient of the material to this. The friction during, that means the friction coefficient during confinement application. And we talked about this. If you, while you're squeezing it, if the friction coefficient is high, it'll pack to a system that's not quite as dense. If the friction coefficient during that is low, it'll pack to a denser system. Okay, so that's boundary contraction. We typically only use that if we're doing a granular system with the linear model. What we do instead when we're building bonded systems is we typically usually do this grain scaling. And what this does is it always keeps the friction zero, so we get the densest state. And what we do is we iteratively scale the grain sizes. So think of it, it's all packed, it's under high compression. You then go and say, multiply all the radiuses of the grains by 0.99. So now they're all smaller instantly. And then it's going to rearrange and the pressure will drop. And then if we make them smaller again, it'll rearrange and the pressure will drop. Conversely, if you need to get a higher pressure, these things get scaled upwards. Okay. And so there's an iterative procedure that does that. So basically then because we're doing that with zero friction during that process, we get a dense packing. Okay, which is usually what you want as the starting point for your putting in glue, putting in bonds. That's what I mentioned. If you, during this confinement application of boundary contraction, if you set that to 0, you'll get the densest state. If you set it all the way up to the material, the actual material friction, you'll get a looser state. Okay, this is what was done in that pavement design package work. This was the parameter that allowed us to have some control over the initial porosity of our system. Okay, which is a really important thing for granular response. So then there are parameters that control the packing process. So one of them, seed of the random number generator, right? We talked about that and why we want to do that, right? Look, it should be greater than or equal to 10,000. Default is 10,000. It's an integer, right? Material pressure that you're packing it at, right? Pressure tolerance. Remember, it's going to do this iterative scheme until the pressure that it measures is equal to the pressure you specify. So there has to be some tolerance of how close you get. So this is pressure, current pressure minus the target pressure. Take the difference of that, how far you're off, divide it by the target pressure if that's less than epsilon. All right, so that's a tolerance for that. This is the super important one. Epsilon limit. This is the parameter that's getting fed into, you take a system and you have to cycle until you believe it's in static equilibrium. And we do that using the model solve ratio average command. So that ratio average command takes a parameter. We've typically been using 1e to the minus 5. So this is the equilibrium ratio limit, the A ratio limit that is going to be used during this process, right? As we keep on doing something and we need to cycle until we get to equilibrium, okay? During this packing process, notice this default is not as tight. It's not 1e to the minus 5. Because as we're iteratively doing these changes and coming back to equilibrium, we don't necessarily have to go all the way till it's totally perfectly in static equilibrium, okay? Step limit, if it's doing this iteration and it does more than this many steps, it's going to say sorry. And when this is when it's trying to come to equilibrium. Right? Are you doing boundary contraction or grain scaling? That's what this one is. And this here is this cloud porosity. And depending upon if you're doing boundary contraction or grain scaling, these are the default recommended numbers to use in 3D or 2D. These are such that you're going to get what you want is enough grains in there to be reasonably well packed at the beginning, and then allow the algorithm to iteratively work on that. Okay. These numbers would be different if these weren't spheres, and you would have to then do that yourself, okay, to get that initial decent packing. During boundary contraction, right? That's the mu CA. This is the servo velocity limit. D table 9, basically that there's going to be servos on the walls that are going to be moving to maintain a pressure you want. That's a limit. In case it's not touching at all, the walls are going to suddenly move. They have to move at some velocity. That's the limit. Usually doesn't. You'll see, you can use the default. We've talked about the random number generator. That's going to affect the particle arrangement. So here we go. Material property, material parameter, material MP params. So it's got the same sort of thing inside that data file. Inside here, you're going to set those values. And then there's going to be the same thing, MP list microprops. So now it's going to say material microproperty packing group. These are all those different parameters and what their values are that it's using. Okay. So now you're going to get a packed system. In these data files, I'm only listing parameters that do not have defaults or that I want to specify something different. So this is typically what you would be doing. You would only be setting these guys. Sometimes you might have to go in and change those defaults for certain reasons. Okay, let's actually do this thing with PFC 3D. So I'm going to run this thing. So what I'm going to do, so in this BPM lectures, there's a directory called fist package. Inside that directory, what do we have? We have fist package cover.pdf. That's just this thing, right? Shows you where I got this from. This is what you will get when you go and download. You'll get a zip file. When you unzip it, you'll get this fist package 7.2. Everything is in there. Okay, that's what you'll get. So what's it going to have? It's going to have public mods.txt. This is the public modifications list. So it's going to say, oh, fist package 7.1. It was tested with PFC, this version on this date. And here's what it did. Here's 7.2, added the ability, blah, blah, blah. So every time the fist package gets updated, this 7.2 becomes 7.3, etc. So that's all listed in here, okay? Directory contents. This is discussing the contents of every single directory underneath here and what it's doing, okay? There's a README at the top. This talks about the package. Here's the general capabilities. Here's the layout of it. Here's an example where the example projects are. Documentation, installation notes. No, there's no installation notes. You don't have to install the FIST package. Unlike the program, there's an MSI file. You got to install it. This FIST package is just a bunch of fish functions, so there are no installation notes. You just put this somewhere and start working with it. Now, there's documentation and then there's example projects. So let's look at documentation. So FIST package documentation, here we go. Here's a description of the different documentation and the different things that are in there. This top one is the FIST package memo that describes it all. You know, there's all kinds of other stuff in here too. Okay. So FIST package memo right there. Material modeling support for PFC, FIST package 7.2. Here's the capabilities in one paragraph, all the things you can do. Here's the index, right? Different things you can do, right? Material genesis, there it is. Material vessels, page 47. Let's go to page 47. It talks about the material genesis procedure, talks about the vessels. There's my vessel parameters. There's my vessels. You've seen this, okay? Material genesis procedure. It talks about the procedure I went through, packing phase and packing parameters, right? All this other kind of stuff, okay? So that's in there. That's your roadmap of everything. There's also, in case I forget to mention this, there's a document in here called calibration of the flat jointed material. And this is actually a step-by-step instruction of, okay, how do I calibrate it to behave like a sandstone? Start with the one in the example, decide on specimen size, fix the microstructure, blah, blah, blah. Do this, you know, keep stuff, do this, do this, do this, do this, and then we can match these different things, okay? Just in case I forget that, that's going to be a very useful one to you if you're building bonded systems. Okay, this package 7.2, documentation. We looked at that. Example projects. Here's the example projects. Material genesis of the linear material. There it is. That's the directory. I want to build a linear material like this, so it's just granular. And what I want to do is build it with two different values of this friction during confinement application. Okay, and I'm going to do the friction of 0, so I should get a porosity of about 0.38. But then if I have a higher friction during the boundary contraction, it's going to lock up at a higher porosity. So let's see how I would do that. I go in here, MatGen linear. Okay, first of all, before I do anything, this is what that's exactly what I took off the website. That's my entire package. I'm going to copy it. I'm going to paste it. And this now is what I'm going to work with. So I don't destroy the thing I started with. So I'll call this .work, -work. Okay. So I'm going to go in there, go into examples, MatGen linear. What do I see in there? I see some projects and I see some data files. Okay. So material genesis, and these are going to be both for 2D and for 3D. They're all together. So material genesis for 3D, that's what I want. So I'm going to open this project with PFC 3D. And what are you going to see? matgen.p3d. Remember, F name and a file. Here then is a description of the material genesis. What's the input to this procedure? Material vessel parameters and material property parameters, those two data files. Those data files are here, material vessel parameters, material property parameters. And then it's saved. It's going to output. It's going to create a log file, which is going to have echoed. It's just a big text file with echoed of all the different things PFC has done, all the commands it's given and run, and then these save states. So it's going to create something called blah-mat-v, which is going to be the material in the physical vessel. The walls are still there. Then it's going to have another save state test, just -mat. It's the material after it's been removed from the physical vessel. This only applies to bonded materials. If it's a granular material, we don't want to remove the material vessel or it'll just fall apart. So here's what this looks like. You would typically never do anything with this file. Okay, this is the file you're going to execute. So notice it's doing a model new, and here it's calling in different data files that it's going to use. Okay. So one of them is this ft.fish. This is the implementation of the fish tank. Okay. It's a whole bunch the fish functions, right? Material vessel volume, return the volume of the material vessel, blah, blah, blah. Okay. So these are all the different fish functions that are being used at this point to create the material. Okay. The typical convention in here is I try to use two things. So this means it's related to the material vessel and it starts with the underscore, which is kind of like, this is sort of like an internal private thing. There's higher level things that don't have that are being called. So that's what it's doing. Doing everything by just calling these 5 fish functions: material vessel make, material properties make, and then it's listing out the material vessel properties, listing out the material properties, and then listing out also microstructural properties. For example, what's the porosity of this final system? What's the average number of contacts per grain? Things like that. Then it's just saving the project. It's turning off the logging mechanism that was being written to this log file. And then it's doing a program exit, and then it's ending this, okay? We'll talk about why it's doing a program exit later. What program exit is going to shut down. PFC is going to shut down, okay? Well, let's talk about it now. It's always good to talk about things as soon as they come up. So hold this in your head. There's also a directory, a project here called Material Genesis and Test -run. Oh, what the heck is that? So I'm going to open that project. Now, it's just this. What this is going to do is it's going to open the Material Genesis project and run it. It's going to close that project. It's going to go down to the compression test directory and open the compression test project and run it. Okay. So this is the high level thing. I can just call this thing and it's going to do these different steps. Okay. This is what I would do. I get everything set up and as you'll see for like the bonded materials, it's going to generate the material, then it's going to do a tension test, then it's going to do a compression test, then it's going to do a Brazilian test, okay? So this is a high level thing. This system clone is, here's PFC running, okay? This is going to go and actually start up a brand new PFC and feed it this data file, and it's going to run. At the end of this data file, it has to shut itself down. That's why there's the program exit. And once it shuts itself down, it goes to the next one, opens the next project, does everything, shuts itself down. That's how it's able to do this one at a time. Okay. Now this is the whole thing. Okay, so let's take out this program exit so that it doesn't shut itself down. Material Genesis. So in here, material vessel parameters. Cylindrical vessel, 240 millimeters high, 170 millimeters diameter. There you go, 240, 170. Effective modulus 500 MPa. Okay, I'm setting those parameters. I'm defining my box. Material property. Here's all these common properties. Here's my packing parameters. And then here's my linear properties. If you remember, for the linear model, we're not specifying Kn, we're specifying the effective modulus, and we're specifying a K ratio, and then the friction. So this will be the final set of properties, right? So for our case right now, friction during confinement application is 0. So this should give us the densest possible state. So I'm going to run this. There's plot material vessel. Here we go. We can watch it running. Here's the number of steps. So it's cycling and now it's contracting. Can you see it contracting? Probably can't really see it, but it is actually contracting. Oh, one of the views, mean stress. This is different ways of measuring the mean stress in the system. I told it to do a mean stress of 150 kilopascals. And so it's trying to get right there at 150 kilopascals within some tolerance. And so that's what it's doing now. And it's constantly adjusting the boundaries to try to get to that pressure, to get to that mean stress. Okay. And so it's happily running it as we're going. And now it's trying to do a solve. And now it's done. So there's my system that I just built. It took 11,264 steps, but notice it's all automatic. In the vast majority of cases, this automatic stuff will work. Okay. So there's my packed system at 150, right there. There's two different ways of measuring it. I'm measuring it with, and we'll talk about this later. One way I'm measuring it is I'm putting measurement spheres in here and asking for the stress from those. Another way is I'm taking the force on the walls and dividing by the diameter, for example, by the circumference, for example. Those are two different ways of measuring stress. I'm using the measurement, the wall-based one is the one I'm using to try to get to 150. Okay. So this thing actually, the stress got higher and higher. So the walls actually moved in this system to be able to contract to get to this. And so now at this point, in here, it said material property list microstructural props. So I'm going to run that. I'm just going to run that. So I'm going to select it. I'm going to go up here and this little button, execute the selected command. Boom. There, it executed the command. MP list microstructural props. So what did the command do? It echoed stuff to the screen. Material microstructural properties. So grain size and packing information. Number of grains, 835. You can see the grain size distribution in one of the plots. Document, plot, grain size distribution, layout wide. There. Grain size. It's going from 1.4, 14 millimeters to 20 millimeters. That should have been the material property I specified right here. Lower diameter, upper diameter, volume fraction of 1, 14 to 20 millimeters. There it is. That's my grain size. This is mass pathing from 0 to 100, right? What else is the microstructural properties? Average grain diameter, 17 millimeters. Median grain diameter. This is the value at the D50 point of the size curve. Vessel resolution. How, given the average diameter, if we take the width of the vessel divided by the diameter, how many grains across? About 10. There's about 10 grains across here. Okay, that's always an important parameter in these types of systems. You want to know that. Measurement-based porosity. There we go. 0.38. Write that down. 0.388. 38. What is it? 0.38. 0.388. That's from the measurement sphere coming back. Okay. Number of active. These are linear contacts. 2408. 2,000 of them are grain, and some of them are grain wall. Right. If we looked at, first of all, here's the force chains in that system. They're all compressive. We add a plot item, looked at the contacts, and now let's do this by color by contact type and make the ball facet ones black. Tell PFC to update itself. There you go. The red ones are the grain contacts. The black ones are the connections with the wall, right? I should be able to look at numeric value. Let's see if it's in here. E modulus, E-mod. There we go. There, it's this 500 MPa, which should have been what I put. That was the 500 MPa. That's what I wanted the internal material to be. And the material vessel, I made it the same. So that's why they're all 500 MPa. Okay. Now I want to run this again, and the only thing I want to do, oh, there's a save file here. Material PFC mat. As you're going to see in this material vessel world, where do I put this? When you set the material properties, this thing is going to be a name that it's going to use. That it can, and so that will control. That name will come here, -mat v, and I don't know why this didn't say AG linear. I'd have to look at that. So what we want to do is run it again, but this time we want to set that to 0.4. And I don't want to set it any higher than 0.4 because that's the final value I'm going to have. So then I just go here and I just run it again. Now you're going to get to watch it, watch those walls push in. Kind of could see it there a little bit. And there's the force chains developing as it's pushing in and as it's trying to get 150 here. Right? So give this a moment. All right, there's my system. You look at those balls, you can see these little dots. That's where they're actually sticking out. There's a tiny overlap between them and the walls, and that's where it's sticking out of the walls. If I make the walls not transparent, that's where each ball is pushing against it, because that's actually a portion of the ball that's overlap, that's sticking out. But I'm making the walls transparent so that you can see inside, right? You're also seeing how the vessel, right? It's got those overlaps just like that picture I showed before. It's done. So now if I look at the porosity, let's see. Porosity 0.418. So it used to be 0.388. Now it's 0.419. So it's a higher porosity. And I got that because I changed that parameter. Okay. So that's the example. So that's the basic idea of using this thing. That's essentially what you're going to be doing.